It is 2 in the morning in the North Atlantic. A destroyer is running a sonar sweep, and the crew is watching the screens with the particular stillness of people who know something is down there. The pings go out clean. The returns come back empty. Nothing below. The ocean appears to be cooperating. Except it isn't, because somewhere beneath that ship, a submarine is running silent, and the destroyer has already lost it. Not because the crew made a mistake, not because the submarine went deeper, not because anything was jammed or broken. The water itself swallowed the signal completely. This is not a story about stealth technology or countermeasures. It is a story about physics, and it runs entirely on temperature. Most people think of sonar like a flashlight. Point it down, the signal bounces off whatever is there, and the echo reveals the target's position. For most of human history, that is exactly what naval strategists assumed. The ocean was deep, yes, but sound should still travel through it the way it travels through anything. Loud enough, far enough, eventually it hits something and comes back. Here is the part that changes everything. Water is not uniform, it has layers. And sound does not just travel through water, it obeys water, it bends with it. The ocean has a temperature gradient. Near the surface, solar energy warms the water across much of the world's oceans. The upper layer sits somewhere around 68 degrees Fahrenheit. Go deeper, past a few hundred feet, and that warmth disappears. The water drops to roughly 39 degrees, and it stays there. That boundary between the warm upper layer and the cold deep water is called the thermocline. And the thermocline is not just a temperature marker, it is an acoustic wall. Here is why. Sound travels faster through warmer water. Temperature controls the speed of sound in the ocean almost directly. When a sonar pulse travels downward from a surface ship, it crosses that temperature boundary and enters water where sound moves slower. That speed change bends the wave, not randomly, predictably, according to the same physics as light refracting through a prism. The wave curves, and below a certain angle, it doesn't punch through at all. It refracts away from vertical, arcs back toward the surface, and the deep water beneath the thermocline never gets touched. That region below the layer, that cone of undisturbed water the sonar cannot reach, is called the acoustic shadow zone, and a submarine inside it is not merely hard to detect. From a surface ship running hull-mounted sonar above the thermocline, the submarine is physically invisible, not strategically invisible, not practically invisible. The physics of the water itself deflects every wave before it arrives. Here is what most people get wrong when they hear this. They assume the protection comes from depth. Go deep enough and the sonar cannot find the target. But depth alone is completely meaningless here. A submarine at 400 feet above the thermocline is fully exposed. A submarine at 400 feet below, it is unreachable. Two boats at identical depth in the same stretch of ocean can have completely opposite sonar signatures, depending entirely on which side of the temperature boundary they are sitting on. The submarine is not hiding in depth. It is hiding in temperature. Now scale this up. The thermocline is not a thin line drawn across the ocean. In some regions, it is hundreds of feet thick, a gradual transition zone where sound bends progressively, creating shadow zones that extend for miles. And it is not static. The thermocline rises and falls with seasons. Solar heating pushes the upper boundary shallower in summer, deeper in winter. It migrates with ocean currents. In the tropics, it sits stable and shallow almost year-round. In Arctic waters, it nearly vanishes entirely, and that geographic fact alone shaped an entire generation of Cold War submarine doctrine. Surface navies understood this, and they had to build around it. The answer was variable depth sonar, VDS. A ship unspools a transducer on a long cable, lowering it past the thermocline before activating the ping. Only then does the sound wave actually reach the shadow zone. The variable depth sonar is not better sonar. It is sonar placed on the right side of the physics problem. The hardware is almost secondary. The geometry is everything, but that still required a ship to be present and actively searching. During the Cold War, the United States went further. SOSUS, the sound surveillance system, was a network of fixed hydrophone arrays installed on the floor of the Atlantic Ocean. Thousands of miles of cable, hundreds of listening posts, all of them sitting permanently below the thermocline, passively recording every sound in the water column around the clock. The US didn't just solve the shadow zone problem, it built a continent-spanning sensor network specifically designed around the acoustic geometry of a temperature boundary that most people have never heard of. Here is the operator decision that looks completely wrong. When a submarine commander knows a surface ship is hunting above, the instinct should be to dive, get deeper, get farther from the threat. But trained commanders often do the opposite. They rise carefully, precisely, to just below the thermocline. Not above it, not through it, just underneath. Why? Because that position delivers two things simultaneously: the shadow zone protection from the sonar pinging down from above, and acoustic access to the water above the layer, where the crew can hear the surface ship, track its movements, and monitor the search pattern. The thermocline becomes a one-way mirror. Sound from below travels up through it more efficiently than sound from above can travel down. The submarine can hear the hunter. The hunter cannot hear the submarine. The instinct is to go deep and disappear. The trained move is to hover in the layer and listen. The Battle of the Atlantic forced this into doctrine the hard way. Allied anti-submarine warfare in the early years of World War II was failing at a scale that threatened the entire supply line to Britain. U-boats were sinking ships faster than they could be built. The early Allied sonar system, acoustic, was hull-mounted. It operated from above the thermocline, and in the North Atlantic, the thermal structure of the water was creating shadow zones that acoustic simply could not penetrate. The U-boats weren't always smarter or faster. In many cases, the physics was just working for them and against the Allies. The post-war analysis of those losses, and the early Cold War reckoning with Soviet submarine capability, drove a complete redesign of naval sonar architecture. Variable depth systems, towed arrays, dunking sonar on helicopters. The thermocline didn't become doctrine from a physics lecture. It became doctrine from the body count of ships that went down in water that should have been watched. There is footage of this that most people have seen without understanding what they were looking at. A naval helicopter hovers over the ocean and lowers a sonar transducer on a cable into the water below. It looks like routine procedure. What is actually happening is that the pilot is physically placing the sensor below the thermocline before turning it on, because activating it from the surface would accomplish nothing. The dip is not optional. The dip is the entire operational logic. And a destroyer running zigzag patterns during an anti-submarine search is not navigating randomly. It is mapping the water column, building a thermal profile of the ocean beneath the hull before deciding where to place its sonar energy. The water temperature charts on the ops room screens are not weather data. They are tactical terrain maps. The thermocline is not a reliable wall everywhere. In storm-churned water, wave action mixes the upper layers and temporarily destroys the gradient. In polar regions, the surface water is already cold enough that the gradient nearly disappears. Arctic submarine operations during the Cold War played by completely different rules. Soviet ballistic missile submarines ran beneath the polar ice cap specifically because that environment disrupted the acoustic geometry that made thermocline exploitation so powerful everywhere else. Different ocean, different physics, different doctrine. Modern submarines carry precision thermistors to locate the layer in real time and position accordingly. Modern surface ships trail towed arrays at depth, continuously sampling the water column. The hunt is bilateral now. Both sides hold better information about the thermal structure of the ocean than any operator in 1943 could have imagined. Back to that destroyer in the North Atlantic. The pings going out clean, the returns coming back empty. The crew watching screens that show nothing. The ocean has an architecture they cannot see, warm above, cold below, and between them an invisible boundary that turns sound into a tool and a trap simultaneously. Every major submarine doctrine written since 1945 is built around a single physical fact. The water has sides. Which side a submarine is on determines whether it exists to the people hunting it. The thermocline is the most consequential military boundary on Earth. It has no coordinates. It appears on no chart, but entire fleets are designed around it. Temperature bends sound. That is the story. But here is the next door. If temperature shapes acoustic detection that completely, what happens when the submarine itself generates a heat signature? Because a nuclear reactor running at depth does not stay cold, and there are sensors in the modern ocean that are not listening for sound at all. They are measuring temperature anomalies in the water column. A submarine hiding below the thermocline for acoustic stealth might be making itself visible to a completely different layer of physics. The ocean does not just carry sound, it carries heat, and some sensors are built for exactly that.